Hi everyone, today I'm going to talk about the elusive universe, and I will focus on the theory, intensity, and precision studies. Okay. So here is an outline of the talk. First, I will introduce what do I mean by the elusive universe, and then I will talk about the theory or the model building parts. That is, I will cover the dark mesons and elastically decoupling relics. Then I will talk about the intensity search, and this is also theoretical, but will have more phenomenological flavor, and I will introduce the Millicharge and forward physics facility. Finally, I will talk about the precision studies that includes the asymmetric probes on dark matter gravity. Okay, so elusive universe. This is a crucial time to plan our future. There's Higgs boson discovered in 2012. So what are the next big things? And this is also a fascinating problems. There's also many fascinating problems remains, including dark matter, gravity, neutrino properties, dark energy, granification, so on and so forth. All of these are very interesting. And if you look at these, there is many of the subjects that were there, many of the content. There's a lot of content in the universe that we don't fully understand yet. And as scientists, we will never stop understanding until we understand all of it, right? Because we're greedy, we want to understand everything. And that is the point of our study, to go forward. So then what are the first things that we can study? So to me, there are three most important things: neutrinos, gravity, and dark matter. So if you wake me up in the morning, these are the three things that I will be thinking about, probably. And what's in common between them is that what's in common among them is that they all have feeble interactions with the standard model. So that's why I call them the elusive universe. And the dark matter, in the theory landscape, there's so many different models. And you will ask me, why do I call this a theory? Because there's so many models. This is not really like a string theory or lattice gauge theory. It's not really a full theory. But that is actually my point. My point is we want to find the ultimate one theory for dark matter that describes all the dark matter phenomenology, and also we want to find the dark matter properties. So all of these models are building blocks to our understanding. And my works, which is featured in this Cosmic Visions 2017, this is a 200 author community report. This work is one of the interesting building blocks that help us to explore the low mass dark matter that will push us to develop new experiments to study, because you need lower threshold to study these low mass dark matters. And there are many other interesting related works that has published after our work, but our work was featured in this report. Okay, how about experiments? So there are there are a lot of interesting experiments that we propose for our future. And focusing on dark sector or dark matter studies, these are the important experiments. And the blue one are the one that I'm involved personally: Dune, Dark Quest, Millikan, and Forward Physics Facility. And the proposed one that the red one are the one that I proposed, includes Long Quest experiment and Formosa, which I'll mention a little bit later. And also notice that there is a major focus or major benchmark that is millicharged. I will also talk about why millicharged particle is one of the benchmark and my contributions on this specific topic. Okay, so let's talk a little bit more about the title. So what do I mean by the intensity frontier or intensity studies? So intensity simply in our context means that high statistics should study elusive objects. So these include neutrino, mini-charged particles, and long-lived particle decays. And the key concept would be putting a lot of particles on target. For example, Fermilab beam can put 10 to the 21 protons on target per year. And you can imagine James Ward-Prowse, who is a football player, and you need a lot of these football players to kick this elusive ball in order to kick it into a high energy or to produce it. And you also need a dense target to catch it, right? So that's the essence of a big part of the intensity frontier. And how about the precision frontier? Precision frontier means that you want to do a precise measurement of quantities. And for example, asteroids are very dangerous, so you really need to track it very precisely. So there are space missions tracking dangerous asteroids. And you can also reach 10 to the minus 20, minus 11 fractional uncertainty. And fractional uncertainty is the type of quantity that we're looking for. So you want 1 meter precision for 1 AU distance object. That's the fractional uncertainty that currently the OSIRIS-REx mission can do to track the Bennu asteroid. And using that, we can actually study the dark matter gravity effect, which I will talk about in the end of the talk. And also you can do a precise measurement of time. So currently the NASA Deep Space Atomic Clock can reach 10 to the minus 15 fractional uncertainty, which means you lose 1 second every 10 million years. And the best terrestrial clock is 10 to the minus 18 fractional uncertainty. And this is a lot of interesting effort. And in the UK, there is this QSNet network that is actually studying fundamental physics using this precision timing. And we also write a paper of putting this deep space atomic clock on board of Parker Solar Probe to study ultralight dark matter bound to the sun, and it's accepted by Nature Astronomy. Okay, so in a big picture, precision and intensity have actually helped us to probe the lower coupling and actually understand better the gravity and neutrino. And high energy is used to study a lot of, probe a lot of interesting theories. So what's the next big thing? One of the next big things is, of course, the dark matter for me. And this is because previously we already understand gravity and neutrino. The next thing we could expect is to find dark matter in either precision or intensity frontier. And I will actually tell you a way to see dark matter just pure gravitationally. And theory is really leading these efforts of both trying to find dark matter and also connecting to the high energy theory, which I will also talk about close to the end of the talk. Also in the beginning and the end of the talk, because in the beginning, I will tell you how we can build dark matter models. Okay, so if you think finding dark matter is a little bit kind of scary task, it's so difficult to achieve, let me remind you of Frederick Reins. He's a professor at University of California, Irvine, which I'm from. And he first detected the so-called undetectable neutrinos, followed by a thorough investigation of their properties. So the reason that he gave why he wanted to study neutrino is because everybody at that time said that he couldn't do it. He and his team couldn't do it, but he found out a way to use the reactor to study neutrino. So let me use this to motivate us that the elusive universe is at the horizon. Let's keep ask deep questions and exhaust every methods to answer them. Okay, so dark meson and elastically decoupling relics. This is Vera Rubin, and he's one of the first people to study galactic rotation curves. And as you can see, on the right-hand side, the particles are moving much faster on the outskirts. And you can actually reinfer the matter, the kind of gravitational matter contents inside. And here is a homework that can help you understand this. So on the left-hand side is a point mass. So you can read that actually give you this kind of velocity distribution of over R that is given by the point mass. On the right-hand side, it's given by the constant density. So these are two very simple examples. And from these, you should kind of get a sense that if you have a velocity distribution based on R, then you can actually infer the gravitational matter. So because Vera Rubin has this amazing observation, that's how we learned that there's actually much more dark matter. Even for example, there's much more matter in galaxy M33 than the visible matter. And using that, we found one of the first evidence of dark matter. And that, of course, is the galactic rotation curve, as we know very well. But nowadays, people actually look deeper into this galaxy and study something called small-scale structures. So small-scale structures are the study of small galaxies like dwarf galaxies, spiral galaxies. Sometimes they even study clusters, but just one single cluster. And you can look into their density profiles. That is depending on the radius to the center. And when we study the small scale structure, we've actually found some problem. This is one of the problems that is called coarse versus cusp problem, that near the center of the galaxy, the simulation of the collisionless cold dark matter tells us that it should be a cuspy profile, meaning that the density is rising up quite sharply. But when we actually feed the data, as previously discussed, we found that it's much more flat. And there are two proposed explanations. One is dark matter interact with itself rather strongly. The other one is, of course, just standard model. You have supernova and other process to push dark matter from the galactic center. So both could contribute. And you can say that maybe you don't need dark matter to do anything weird for that. But why is this so interesting to me is small-scale structure study seems to be one of the very rare handles to actually understand the dark matter properties, not just its existence, because there is this indication that it could interact strongly. So you not only discover it, you also can use it to study its properties. And that's very important. Okay. So moving on, now, once you study these more, you find out that the dark matter is actually the same strength as the proton-neutron scattering interaction in terms of strength. So that is a very interesting observation. And so that's why people consider dark matter maybe around the mass of MeV to GeV, has strong self-interaction. and also has a velocity dependence because based on the data, it seems that the velocity dependence is preferred. So maybe that tells us we should consider dark matter to be hadron-like. And that's why we build a model to model this kind of behavior. So we consider something called dark matter resonance structure, meaning that you have a dark matter mediator for the self-interaction that is about 2 times plus a little bit of the mediator is about 2 times plus a little bit of the dark matter mass. And this induces something called Bragg-Wigner resonance, meaning that the dark matter cross-section will have a peak around a certain velocity. And that when the delta is, in this talk, we'll consider this delta to be positive and small. So the resonance condition will meet when the collision hits the resonance when V is equal to this VR resonance, and then this energy is equal to this 2 delta M. It will hit the resonance and can help explain these small scale structures, right? So why is this so? First of all, this is already very exciting to do that. Secondly, there's also ways to distinguish that from the usual light mediator scattering. That is that when you're in the low mass, you can actually compare them to the data, and they might have different predictions. And they do have different predictions. So on the right hand side, you predict a much lower cross section. On the left hand side, you predict a much stronger cross section. So in the future, you may be able to distinguish them. And another thing I want to mention is, why do I say it's upsilon NS, right? And here one thing I forgot to mention is that the B meson is about half of the upsilon 4s meson mass, and K meson is about half of the phi meson mass. And that's why we use this kind of QCD sector to build this model. But why do I say NS rather than 4s for the dark sector? This is because learning from Chris Quick and John Rosner, we learned that we need to push M heavy quark much larger than lambda QCD, much larger than the lighter quark to hit the resonance easier. And there is actually a lattice, there's also actually a lattice study from the lattice QCD people, but they are actually also part of the UK QCD. So they actually did the simulation, and we can actually use that to also find this kind of vector meson resonance. So just quickly, why do you hit the resonance easier? It's because the 2 times of the mass of these kind of 2 different kind of mass will grow when you push your MQ over lambda to be larger and larger, so it will grow. And the level spacing for this upsilon NS meson is getting thinner and thinner. So when you go up higher, it will be easier to hit the resonance than if you're lower. So that's why it's easier to hit the resonance, right? And so you need your MC prime. So all the prime means these are dark matter particles. So the MC prime, we set it to be the same as MB prime, has to be much larger than the lambda QCD and much larger than the light quark mass. That's how you get this kind of very close to resonance behavior. And in this sector, there will be B and D and lambda and pi eventually can decay through the portals. So B and D will be the dark matter. Okay. So this is the vector resonance. Let me get into the elastic decoupling relic consideration. So strong self-interaction can affect dark matter's thermal history as well. So not only you can explain this small scale structure problem, you can also have a different type of dark matter thermal history. And that especially happens when you have dark matter that has 3-to-2 interaction or n-to-2 interaction, or simply you have number changing processes. So in the existence of these 3 dark matter going to 2 dark matter scenario, you have something called cannibalization. And the original proposal is not completely ruled out, but it's quite disfavored by a large-scale structure study. But today I'm going to introduce you something I wrote, that paper we wrote that is called Elastically Decoupling Relics. And a side note is that the QCD also allows 5 particle interactions, and there are many further consideration. Originally, of course, was considered by West-Zumino and Wheaton. That's something called West-Zumino-Wheaton term, but it has been studied by both. People use it to study for dark matter, and also there's a lattice study for the dark matter kind of model. So there's a lot of interest here, and it would be great to further investigate this type of model. Okay, so the standard freezeout, WIMP freezeout, is that in the early universe, the dark matter is keeping itself as a thermalized particle. It's a thermal distribution. In late stage, after the freezeout, this will usually the dark matter annihilation become ineffective compared to the expansion rate of the universe. And then you find out that the dark matter in the comoving volume will be fixed. You can imagine that you have a box of a particle. There are 3 particles, and you simply expand the box. So the density inside the box will get lower, but the number of particles inside the box is always the same. And this is the same idea. So the number of particles inside this box, which is described by the A to the 3, A is the size of the universe, roughly speaking. Actually, A is a scale factor that quantifies the size of the universe. This n chi times A to the 3rd will be a constant after the freezeout. So this is the usual thermal history for WIMP, and it's called weakly interacting massive particles. Now, there's something that we propose called elastic decoupling relics. That is something different. In the early universe, you will still have the elastic scattering, but at some point, this process becomes ineffective. However, actually, this annihilation actually freeze out earlier, so this become not important. But elastic scattering actually become unimportant, but the 3-to-2 is still functioning. And this 3-to-2 will actually cause excessive heat. So it's called the slow cooling or cannibalization. And finally, after the self-interaction freeze out, you will actually enter the full freeze out scenario. And here is kind of similar to the WIMP. We show you the kind of this kind of thermal history. And here, the m chi times y chi is simply the same as the co-moving number density up to a factor. So you can just think about it as a co-moving number density. So in the early universe, again, you have an exponential drop. But now when you decouple, you actually have a cannibalization regime that your cooling is slowed down. And this slowdown of the cooling is something called cannibalization. So you ask me, how do you understand this? The way to understand this is to say that even though the decoupling happens, you still have 3-to-2, so you will keep your dark sector with a constant entropy, co-moving entropy, constant co-moving entropy. So because you have a constant co-moving entropy, if you solve for the distribution, you find out that the number density is also almost a constant. The co-moving number density is also almost a constant, except it times the temperature T chi, so this should be T chi. T prime, this T prime here should be T chi. And you can solve for the T chi and T chi drop very slowly logarithmically. So it tells you that the number density, comoving number density, actually also drop very slowly until it freezes out. And actually freeze out or not, it doesn't really affect the comoving number density that much. So you don't have to believe in me. We actually solve for the coupled Boltzmann equation, which is very complicated. And this is what I spent 1 or 2 years on, just to help solve this, help develop ways to solve this coupled Boltzmann equation. And this paper, later on, we use a similar kind of code to work on vector fermion elders. So we actually have 2 papers on this, but I'm only listing one of them here. And so the code is tested by 2 different groups. Yeah, so here the only overlapping author is me. So the code has been tested by 2 different kind of groups. Okay. So the direct detection of elder dark matter is very exciting, because this kind of dark matter, the radical abundance, is determined the exact same process as how we can directly detect it. So this is why you have a prediction of this elder model, and there are many, many different probes that is proposed for the future using this novel material to probe them. And also Sensei, dark side, Xenon are starting to try to probe this regime. And Elder motivates low mass dark matter electron scattering searches that are shown here for these germanium, silicon, superconductor, graphene. There are many, many other I'm not listing to search for this kind of dark matter. So there is actually has a lot of paper that has been published after us. They are citing us and probing this kind of dark matter using novel material. Okay, how about why do you have this kind of thing that you can couple to electron? That's because you have something called portals. And these 3 portals are the renormalizable portal, including the dark photon portal, Higgs portal, and neutrino portal. And this was, of course, kind of partially proposed to for the sub-GeV dark matter freeze-out proposed by Lee and Weinberg. There is a bound that you need extra ingredient for the freeze-out. But of course, nowadays, we know there are other ways to get the radical abundance thermally. So this bound is not always valid, but still it gives us some motivation. And I actually proposed with other people that we can use international linear collider beam down to search for one of the portal, that is the neutrino portal. And there's another group also did it in the same time, a Japanese group. I'll add it in the slides that you can see. Okay. So intensity search for elder dark matter is also very important. As I say, intensity is that you have a lot of particles hitting the target, produce this elusive stuff, and see them in the detector, in the dense detector. So as you can actually, after us, this mini Boone curve was published and started to probe this regime. So one day the LDMX will be able to try to probe this regime of the elastically decoupling relic dark matter or the elder dark matter. And Bell also have some sensitivity. So my plan forward is that I want to further study this very interesting model and build a complete dark matter theory motivated by the small scale structure, novel thermal history, resonance dark meson idea that I proposed, or 5 particle dark matter processes that I considered as well. And we can learn the QCD side from the ADS QCD people and holography people. And the previous successful example is the Randall-Sundrum model. Of course, that is more for the gauge hierarchy, Higgs hierarchy. But here, you can use the similar kind of mindset to understand the dark matter thermal history, or the current study of dark matter scattering. Another thing is also, of course, you can also directly use lattice QCD to calculate the quantity of this strongly interacting quantity. And of course, ADS-QCD and lattice QCD already have this kind of very good connection. So I can build these new connections to study these subjects. Of course, there's also extra dimension dark matter resonance that is very interesting. And phenomenologically, it's also very exciting. We should study large observatory, which I study, super hyper K, neutrino experiments, DUNE, and colliders, which is ILC, LHC. And there are many important and dedicated experiments. And so the point is to build new topics and connections for these already very exciting fields. And I think here there's these very strong groups that I can collaborate with in order to find the ultimate theory for dark matter and also understand neutrino and gravity better. And that actually brings me to the next topic, which is, of course, more phenomenological on the phenomenology study of the intensity frontier. Okay, so there are many ways to do intensity search, but the majority of the ways are to study the fixed target. So you can study dark matter, long-lived particles, neutrinos, and many, many interesting topics. And here I propose two experiments. One is the Fermini proposal to study Millicharge dark matter. Another one is the Longquest proposal to study the long-lived particle, and they are both proposed at Fermilab. A slightly different way to study to study dark sector particles is that there's cosmic ray production. Cosmic ray can hit the atmosphere and produce Chi particle, or there's cosmogenic long-lived particle that they can fly into the super Kamiokanda. And that is actually what we study. So we can study again Millicharge particle in super Kamiokanda or hyper Kamiokanda, or the cosmogenic axion-like particle that can be studied in super K or hyper K. And finally, there's so many different kind of neutrino experiments that we can study. And we again study a Millicharge particle and also a kind of dark sector to study this kind of, but this one is using the Minerva to study kind of something very interesting called dark neutrino that is actually a heavy neutral lepton, but can couple to photon, decay to E plus E minus to explain the mini-Boone LSND kind of anomaly. And we use Minerva to probe that type of model. So Millicharge particle has always been one of the main targets for me, but why? Okay, the answer for why is because Millicharge particle is a study of electric charge quantization, and it has been a long-standing question since Paul Dirac. And the empirical charge quantization, of course, motivated Dirac quantization, grand unification theory, and fractionally charged particle is also predicted by some string theories. And when Xiaogang Wen and Edward Wheaton actually wrote a paper in '85, and he actually did an interview, which you can find on YouTube, to say that this fractionally charged particle is actually one of the major signature of superstring theory. And string communication and quantum gravity is also a deep question that Gary, the professor that I have been discussing with, that has been very interested in this. And I know many of you know Gary, so I will mention this discussion a little bit more in the next slide. Conservatively, you can say it's a test of if E over 3 is the minimal charge. And you can define epsilon as Q over E. And from here, chi will be the Millicharge particle for simplicity. And dark matter can have significant effect. Sorry, Millicharge dark matter can have significant effect on CMB 21 centimeter absorption spectrum. And of course, there is this anomaly that is reported by the Edges collaboration. Maybe you heard about it. And I'm not sure yet, and the community is not sure yet, if this is really an anomaly that is from new physics, or if it's actually an anomaly because it could be from the foreground modeling. Of course, the experimentalists try to do as great job as possible, but this is kind of a new class of experiments. So there's still uncertainty, we don't fully understand. So in the future, there will be Tsai and Saras, these kind of experiments that has been proposed. Oh, actually, I will add the references. And these experiments will come on. So it's a very exciting time. And the argument, what is interesting is really that if you have dark matter being Millicharged, then they can affect this measurement significantly. It's not so much about, to me, it's not so much about anomaly. It's about if you have dark matter being Millicharged, it will affect all of these measurements. So we should have a detailed study about that. Okay. Also, deeper theory question is that there seems to be two types of Millicharge particle. One is from the massless dark photon on the left-hand side. One is on the right-hand side, a dark photon without, sorry, Millicharge particle without a dark photon. And that's why Gary and I also chatted with Steve a little bit about if we can actually tell the difference between the two and what kind of string theory topics or string theory compactification or guts that we can actually constrain or have an implication on. So this is an ongoing project, but if you're interested, you can ask me and we can discuss more. And finally, a lot of the contribution that I did are considering the production and detection. So you can produce this Millicharge particle in the Proton machine. You can do it in Accelerator, cosmic ray, and LHC forward direction. They all look kind of similar. You have a PP collision give you meson decay to photon, and virtual photon give you chi bar, which is Millicharge particle. Or you also can have direct detection, direct production. And this Millicharge particle can fly into the mini boon detector and give you electron scattering signature, or fly into the scintillator and give you scintillation signature. And this is a clever experiment developed by Haas, Hill, Adder, and Yu-Dai. And my contribution is that I realized you can place this kind of detector, but in a different location to drastically improve the sensitivity. And that I will give the example in the next slide. And we wrote two different papers, one in the neutrino type of experiment, the other in the kind of the forward LHC forward experiments. So this is the place that can host this kind of experiment. That is something called a forward physics facility. Because in this kind of place, you can have high energy plus high intensity. So you can have maximum fun. And while, of course, we're thinking about future collider, which can be many, many years from now, could be a long wait. We, of course, should first maximize LHC. And these studies are very complementary to the exciting Higgs dark matter study in the main Atlas CMS detector. So there has been several experiments that can be hosted in this forward physics facility. And my contribution is that I realized if you move this millican type of detector in the forward region, because there's large meson flux, you can significantly improve the sensitivity of LHC in Millicharge particle. You can see that here is a 3 order of magnitude improvement. And also just comparing to Millikan, you're also better. You have 1 or 2 order of magnitude improvement from the Millikan experiment. So this is very exciting and we're pushing for it. And it is actually going forward. So forward physics facility has been giving several preliminary green light to go forward. That there is already preliminary not preliminary, there's already funding for several of the detector for the R&D, including there are Simon's funding, and I think Brookhaven National Lab also have LDRD that is supporting the development of some of these experiments. And also my collaborator also have some experimental collaborator also have some startup money to help push these Formosa. I forgot to mention the name. So putting this forward, I call this Formosa because it's a forward Millicharge search. Yeah, Formosa here I also say forward Millicharge search. And for microcharge search because we want the Formosa name. So we're pushing these forward, and actually CERN civil engineering team already considered all location and decided that this location is the best. And this is also a little far away from the RHC beam, so there will be less background. So this is the updates. Okay, and you can also study neutrino, of course, and this is in progress. So finally, I want to say that there has been tremendous progress in the Millicharge particle and Millicharge dark matter studies. There used to be this empty space, and now it's filled with accelerator search, direct detection search, which I don't have time to talk about. And also the green ones are the Millicharge dark matter model that can affect the 21 centimeter absorption spectrum. And CMB 21 centimeter study is really kind of the future for them because they can study a lot of other interesting topics that previously cannot be studied. So this is, of course, one of the very exciting connection to the future of the cosmology. Not just the kind of particle cosmology for dark matter, but the cosmology, like those are very observational CMB, S4, those kind of cosmology. So Millicharge particle has interesting theoretical and cosmological connection and is a benchmark to compare accelerator experiments. And I have made a significant contribution in putting a lot of these curves, including Super K, LSND, Fermini, microburst, flare, and Formosa curves are all from our work, or from my work. From my works, yeah. Okay. Finally, precision. Astrometric probe on dark matter gravity. And here I want to combine the lessons I learned from Vera Rubin and from Albert Einstein. And here there are so many objects that can be tracked and can be used for our studies. So as I mentioned, there are NASA experts that including Davide Farnocchia, who is my collaborator. We are very good they are very good in tracking asteroids, and they actually send a mission called OSIRIS-REx to track the Bennu asteroids. If you assume dark matter to be a constant and spheric symmetric around the sun, then when your asteroid is passing through it, it will give you a gravitational force. So by studying this asteroid very, very precisely, you can impose a constraint on the dark matter density purely gravitationally through the study. And this is a preliminary plot. I would, so yeah, you can see that the best one is from Mars is 10 to the 4 times higher than larger than the galactic dark matter. So here is the galactic dark matter, and we're adding the Bennu, Apophysis, and many of these purple dots. So we can set a new bound on local dark matter density, but the downside is that it has to be very much higher than the galactic average. So one day we hope we can use quantum sensor to push this all the way down to the galactic average. And also we can consider dark matter standard model long-range interaction, and only 4 orders of magnitude stronger than gravity. So it's very exciting. So either you go the way of improving the precision, or you say that let me consider some theory that actually have this kind of large effect. So you actually can set a meaningful bound, or you can actually try to search for this kind of theory. And this also applies to cosmic neutrino. I will have not too much time to talk about it, but our bound is comparable to the best lab bound from Hadron. Okay, finally, here I show you a lot of different topics that we can further study. And the first one, of course, has already been accepted by natural astronomy, is putting deep space atomic clock onto Parker Solar Probe to study ultralight dark matter bound to the sun. The second one I just mentioned, that one is coming out next week. And if you're interested, you can further search for my name on YouTube to find that there is this interview that I did that is about the study of the fifth force, which is on the right-hand side, the dark matter fifth force. Sorry, not dark matter fifth force, the fifth force that is beyond standard model that can be tested through the asteroid tracking. There's also, of course, GR modified gravity models and gravitational wave that has been studied by other people, and also primordial black hole topological defect that I am working on. So there are many, many interesting studies. And yeah, again, I will add more references in the slides that I will send out. So here is a summary of the talk. Many of the dark matter studies focus on using the weak interaction to do the WIM kind of dark matter before kind of many years ago. And these are my contribution. Today I talk about my contribution of making the dark matter colorful, right? So having the color group that allows resonance dark meson, elastically decoupling relics. Also, I'm leading new directions at the precision frontier. These include the solar space study plus quantum sensor, and these are collaborating with NASA and ESA people to study the dark matter gravity effect. And also there are Millicharge searches that one proposing that is studying this U1Y sector to have a strong probe of Formosa and Forward Physics facility at Formosa at the Forward Physics facility that has a deep connection to theory and connection to deep theory and cosmology. And we can apply these similar techniques to all portals. And finally, so let me so yeah, so here also the resonant dark meson, it can help resolve the small scale structure problems. It gives you a natural mass scale and strong interactions, and can be linked to the new lattice QCD and ADS QCD studies, which there's a strong group here and we can collaborate on. And finally, there is elastic decoupling relics that give you us new thermal history, new predictions for direct detection and accelerator experiments. And I show you also the future projection. So there's active studies here. All of these are the elusive universe study that I talked about today. Thank you. And we should exhaust every ways to answer the deep questions about the elusive universe. So I will keep on these slides so you can ask me questions. Thank you.